Hello friends, today we will solve another lead code problem and it's called container with most water, and this is commonly asked in Facebook and Google, but it's also asked in other software interviews. So let's see what is the problem. So this problem says that you are given some bars. These are of different lengths and you are given an input array. So these denotes the height of those bars. So you can see this is of height 1, the second one is of height 8, then 6, 2, 5, 4, 8, 3, and 7. And your task is to select any two bars between which you can fill water, and you have to find such two bars such that maximum area is covered. Imagine this is not a 3D container, or you can imagine a constant width container. So width is constant. You are looking from this side. So you are trying to maximize the area, and you can multiply by width to get a volume of water. So you want to store the maximum volume of water. So which two bars or walls you will select. So there will be one left bar, one right bar. So you don't know which is the best. So you will start with, you will take the first bar, and the second will be the rightmost bar. And the width will be this. The size of this is 2, 4, 6, 8, 9. So 9 minus 1, 8 is the width, because if you have 2, then you have a width of 1. So here you have 9 bars, so width is 8. So this is the width. And now what will be the height of water? If you have a bar of height this and another bar of height this, maximum level of water can be this, whatever is the minimum height, because if it goes beyond that, it will overflow. So whatever is the minimum height, that is the height of water. So initial area will be min height, I can denote by h min, and max height I will denote by h max. So h min times width. This is the initial area. So you have taken the maximum possible width. You cannot make it wider. But this may not be the maximum area, because there may be some smaller width bars which are at smaller width closure, but they are very high, and so the overall area can be more, but you don't know that. So you are looking for a smaller width. Then what you will do, there is no point in keeping this minimum fixed and moving this, looking for a bar higher than this maximum, because minimum, the height of water is governed by the minimum wall. So unless you increase it, you cannot gain by decreasing the width. So if you decrease the width but you don't increase this minimum, you will get a smaller area. So only way to increase your area by decreasing width is to find a bar which is higher than this minimum. So this minimum can be left side also, right side also. Maybe this bar was very tall and this was small. So whatever is the case, if min is smaller, then you move to the right until you find a bar which is higher than this min. So in this case, you reach here and this is higher than this min. So this pointer moves here. So you are no longer pointing to here. Now you have two bars. H max you did not move because there was no point in moving that. You need to increase the H min. Now you will compare this new height and H max. Whichever is smaller will be your new H min. So in this case, this H is H max, and this H max becomes H min because it is the smaller of the two. Now your width has become from 9 to 8. So let's write the absolute numbers. It was 1 times 8 So new area is again h mean times width, but width is now 7 and minimum height is 7. Maximum is 8. So it will be 7 times 7 equal to 49. And you will compare if this new area is better than earlier max area or not. It's better. So you will keep track of a max area, area max, and you will store there whatever is the maximum you have gained so far. So you will update it only when you find a better maximum. So we have achieved 49 till now. Now we will repeat our argument. So there is no point in moving the maximum because you will be decreasing the width, and the only way you can increase the area is by increasing your minimum. So if we look for the next bar which is to the left of this min and higher than this, so we reach here. So our new index is this, and we compare this with earlier, the max. So if it's more than max, we will update max and min. But in this case, it's not more, it's equal. So we will not change. So this is our new h min. So new h min is 8. And width now has decreased by 2. So it's 6. So new area is 48, which is not more than a max. So we don't update it. So width is 1, 2, 3, 4, 5. Sorry, width is 5 in this case. 4, 5. So in fact, it's 40. Because earlier width was 7, we decreased by 2 here. So 40 was not better than 49, so we don't change it. Now we can move any of these. So we look for a bar higher than this. And in this case, we will not find it. We will reach till h min. So when h min and h max indices become 0, become same, that is width becomes 0, then we stopped, because when width is 0, area is 0. So in this case, we got the solution as 49. Now let's write the code for this. So this is exactly the same problem. And this height is this vector of heights. So let's write whatever we had discussed. Min height. So let min height is first height, max height, last height. Similarly, we keep track of index. So we roughly arbitrarily assume this is the min, this is max. And now we will check which of these is smaller. So if first bar is smaller, then we don't need to change this. This assumption is fine. But if this bar is taller than the last bar, we will flip these values. So now this will become min and max if this is the case. Now what we will do, we will find the width. What is the width? So width is height dot size -1, and max area will be min height times width. Now we have taken the base case, that is the maximum width case. Now we will change our minimum height and minimum index. So while width greater than 0, so we will look for all possibilities. So we have created a temporary index to min index, and until we find a bar which is higher than this, strictly higher, even if it's equal, there is no point in changing the minimum, because we have decreased width but we have not increased height. So only when we get an index so unless we get a strictly higher height, we don't change the index. And this is just to keep track that whether the min index is the right one or the left one. It can be towards the right or left. So if it's left, if the left bar is smaller, then we increment the index. If it's on the right side, we decrement the index. And finally, we will do width minus minus every time we change the index. And we also need to check that width does not become 0 or negative. So as soon as it becomes less than 1, we break out of it. We don't need to check further. Now what we need to check is if this newer height, it may be more than the earlier max also. So if it's more than earlier max, then simply we will change min height equal to max height. So earlier max becomes min now, max index, so it's idx, and this is also idx. So we are just keeping track of whichever is minimum, make that min height, and whatever is maximum, make that max height. Else, max height will remain unchanged. The newer height is the min height. So min idx equal to idx and min height equal to height of this index. Max remains unchanged. Now after that, we take max area equal to max of max area and W times min height. So this is the new area. We compare with max area and update accordingly. And then we need to return this max area. Let's run it. there is no width. I had taken W. I hope I have not used width anywhere else. Okay. Okay, here also I have done the mistake. It would have been better to change this W to width instead. So it passes for our case. So let's submit whether it passes for all other cases or not. So it works for all the cases, and our solution seems to be quite efficient because memory is better than 100% and time also better than 95.35%. So it's on the higher end only. So let's try once more. So it remains same. So it looks quite efficient, and you can see what is the time complexity. So you calculate an area and then you keep moving the one of the indices and you stop when they meet each other. So you are not doing more than one scan of this vector. So it's order and time complexity.